Recording in progress. Now we are here in the third video of chapter 10, which is the rigid body rotational rotation about a moving axis. So if you have a rigid body which is ro- rotating at the same time translating, we denote that the kinetic energy of a rotating and translating rigid body is equal to one half times the mass of that rigid body times the square of the velocity center of mass plus the one half times the 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 center the moment of inertia around the center of mass times the angular velocity. Okay, okay. If the motion of this tossed but button can be represented as a combination of kanakay button. Okay, so we have here the rigid body rotation about, so we have E translation plus the rotation. So the kinetic energy in that situation is given by this formula. Another situation is that if you have a rolling without slipping, so the motion of a rolling wheel is the sum of the translational motion of the center of mass plus the translational motion of the wheel around the center of mass. So the condition for the rolling without slipping is equal to the V center of mass is equal to R times the angular velocity, the radius and the angular velocity. And we also have the combined translational and rotation, is the dynamics. So excuse me, we have the acceleration of the center of mass of rigid body. The net external force of an object is equal to the mass times the acceleration of the center of mass. And we have here the net torque of the rigid body about the z-axis through the center of mass is equal to the moment of inertia of the rigid body about the z-axis times the angular acceleration of the rigid body about the z-axis. So this is true as long as the axis to the center of mass is an axis of symmetry and the axis does not change in direction. So we have here a particular example, which is excuse me. So you make a primitive yo-yo by wrapping a massless string around a solid cylinder with mass M and radius R. Okay. You hold a free end of the string stationary and release the cylinder from rest. Okay. Okay, let me. So the string unwinds but does not slip or stretch as the cylinder descends and rotates. So using the energy consideration, find the speed v cm of the center of mass of the cylinder after it has descended at distance h. Okay. So since this is an energy conservation, so if we recall that the K1 is equal to the U1 plus this is equal to K2 kinetic energy final minus the potential. So we have the potential. So here we take this one as at y, okay, y is equal to 0, and in this particular y is equal to h. So here the kinetic energy in this part, so we have here the 0 because it's not rotating yet and it's not translating yet. And in this also in this direction, our potential is equal to 0 because y is equal to 0. So we're left with mg, okay, y1 is equal to k2. Here our k2 is given by the translation plus the rotation. One half mv center of mass squared plus one half, okay. So what this is our formula plus one half as I omega squared. Okay. I center of mass omega squared. Okay, so here okay. So here we have the I, okay, I is equal to 1 half m r squared. So what else? So this is also a situation where the condition rolling without sleeping. So we have B center of mass is equal to R omega. Okay, so we have B center of mass equals to R omega. So and we have the angular velocity is equal to V center of mass times over R. So in this particular problem, your K2 now will become 1 half m V center of mass squared plus 1 half, we have 1 half m r squared times V center of mass over R, okay, squared. Okay. So can you cancel something? Okay. So our keto, so I think we can cancel. So this is a big letter M. Okay, I'm sorry. This is a big letter M. Also, this one is a big letter M. Okay. Actually, we can cancel this. One half times one half is equal to one fourth. Okay. And we can cancel the R. Actually, we cancel the R. So we have 1 half M V center of mass squared plus we have 1 fourth M V center of mass squared. Okay, 1 fourth plus 1 half. So we have 0.75 or one third or three fourth. 0.75 M V center of mass squared. Okay, or 0.75 is equal to 3 over 4. Okay. Uh, okay. Okay. So find the speed. So we are actually interested in the finding the speed. Speed. Okay. So we have here from this equation, mgy is just equal to 3 fourth over m b center of mass squared. Okay. In this case, you can cancel this one, and we have b center of mass is just equal to plus and minus the square root of this one, uh 3 fourth, 4 over 3, okay, 4 over 3 g times y1, which is equal to the uh plus and minus the square root of 4 over 3 g times h. Okay, so that is the speed, okay, of this that is the speed bcm at the center of mass of the cylinder. Okay. So we also have this example. I will leave this example to you. So the race of the rolling batteries. Okay, so let's go now to the example of a acceleration of a primitive. So this is the combined combined translation and rotation dynamics. Okay. So we have a primitive yo-yo in example figure 10.18a. So find the downward acceleration of the cylinder and the tension in the string. Okay, so we're asked to. Okay, let's consider first the Newton's second law. Okay. So is this is accelerating. Fy around Fy is just equal to the mg minus the tension is equal to m or m times the acceleration along center of mass along y. Okay. And also our net torque along z is just equal to the tension, only the tension is doing torque. So the T times R is equal to I center of mass times alpha Z. So we have T R is equal to 1/2 M R squared alpha Z. Okay. So here, okay. So actually we can use this again, rolling without sleeping, which is R omega Z. If you derive this one, the derivative of this one is just equal to the acceleration. The derivative of this one, so this is actually equal to R, and then this one will become alpha Z. Okay, so this is a condition rolling without sleeping. Okay. So from here, tension, okay, tension is just equal to 1/2, okay, this is 1/2 M, okay, M, so we can cancel this one and this one, 1/2 MR, MR alpha Z, okay. So here, and so 1/3 mg, okay. So to find this one, so this in this particular example, so we have m times g minus 1/2 m r alpha z is equal to we have m times r alpha z. Okay, so so we have mg, so we can cancel this one. Okay, we have g is equal to r alpha z. They still have is equal to plus 1/2 r alpha z. Okay, so here z is equal to 1/2 plus 1. Okay. So 3/2. Yeah, so we have 3/2 times g is equal to 3/2. I don't know if I'm doing this right. Al alpha z. Okay, actually we want to find the what is our target here is the downward acceleration. Okay, so if uh, we want to find the downward acceleration and z is just equal to, so here we have alpha z is just equal to 2/3 g over r. Okay, so here we have r and we have 2/3 g over r. Okay, cancel, we have our acceleration is just uh, so let's wait. Can you wait for a minute? Acceleration is 2/3 g. Okay, is equal to 2/3 g. Okay, G. That's this a center of mass y. Okay, 2/3 g. Because 3/2 to 2/3. Okay, so this means that uh, our tension is equal to so so our tension, since our tension is uh, one half m uh, r alpha z. Okay, so we have one half m. So this is actually ACM minus y. So one half m times 2 third g. Okay, so we have 2 over 6. Okay, if I'm not mistaken, 2 over 6 mg or 1 over 3 mg. That is our tension. Okay. I hope you can, you can, what you call this one? I hope you can follow this one. Okay. Okay, so we have another example. We have a bowling ball rolls without slipping down a ramp, which inclined at an angle beta to horizontal. So what are the ball's acceleration and the magnitude of the friction force on the ball? Treat the ball as a uniform solid sphere, ignoring the holes. Okay. So we have here the free diagram of this bowling ball. We have the normal force. Okay, we have the friction. We have the weight. It has the components mg cosine beta and mg sine beta. Okay, bowling ball. So we have a condition, it's rolling without slipping. So from the uh, Newton's second law, we have mg, okay, sine of beta minus the friction plus the negative friction is equal to acceleration a or m. So m a center of mass along x. Okay. Also, the definition of the torque along z. Okay, it is is just equal to, so in this case only the friction force is doing work. Okay, F R equals to I center of mass alpha z. This is equal to for the the for the sphere. So we have 2 over 5 m r squared alpha z. So this is the moment of inertia for this one. Also, we're gonna use this a center of mass along x, which is equal to r. So this is the condition that rolling without slipping. Okay, what is our target variable? What are the ball's acceleration and the magnitude of the friction force of the ball? So take the ball. So what is the acceleration? So here, Fr is just equal to, so R 2 over 5, we have M R, then we have a center of mass along X. Okay, that is our Fr. Okay, so from the equation 16, so we have unknowns. So we will solve for X, a center of mass. Okay, so for example, we're gonna cancel this one. Cancel. So we have our F now. So we have mg from equation 1 sine of beta minus So we have F, we have, which is two fifth, M A center of mass along X is equal to M A center of mass along X. So we can cancel this one, cancel this one, cancel this one. So uh, we have G sine of beta is equal to uh, A center of mass along X plus 2/5 A center of mass along X. So we have 1 plus 2 over 5 A center of mass along X. Okay. So we have 7 over 5. So we have this is equal to 7 over 5 A center of mass along X. So we have A center of mass along X is just equal to 5 over 7 G sine of beta. Okay, this is our uh, okay for our friction. Okay, friction. So since this is our friction is equal to 2 over 5 m times this one times 5 over 7 g sine of beta. Okay, so cancel. So we have 2 over 7. So we have 2 over 7 m g sine of beta. So in this particular example, you can find the friction and you can also find the center of mass, A center of mass. So this is the end of our third video. So please watch out for our fourth video of chapter 10. So please click the like button and subscribe to our channel for more videos like this.